Morning. My name is Lauren Kirk, and today my thesis partner Phoebe, Garrett, and I will be presenting on our senior thesis entitled An Opportunity Cost Analysis of Alternative Fuels on a Transportation Industry Network. Before we begin, we'd like to make some acknowledgments. We'd like to thank Professor Board, our advisor, for his continued guidance throughout our thesis process. We would also like to thank Dean Werner, our reader, and Professor Harris, our editor, for their help with our written thesis document. I'll begin with an outline. First, I will discuss the background and state the objectives of our thesis. I will then go over the theory and methodology and pass the presentation off to Phoebe, who will discuss our results and conclusions and give recommendations for future work. Greenhouse gas emissions are emissions which remain in the atmosphere and absorb heat energy, contributing to global warming. The transportation sector accounts for 28% of GHG emissions in the United States. Within the transportation sector, ships account for 3% of GHG emissions. To address concerns about GHG emissions in the maritime industry, the IMO has set the goal to reach net zero GHG emissions by 2050. One strategy the IMO has set forth to reach this goal is for the use of alternative fuels to represent at least 5% of energy in shipping by 2030, striving for 10%. At its core, decarbonizing transportation is primarily a fuel challenge. Based on the 30-year projection of growth given by the DNV, the vehicle fleet will grow from 1.2 billion to 2 billion vehicles. This projection predicts that sea cargo per tons mile will have a 35% growth. You can see this growth projection for the maritime industry on the dark blue band on the graph, measured as yearly energy output. The existing transportation infrastructure, including tankers, pipelines, refineries, and gas stations, is oriented towards oil-based fuels. This infrastructure will need to change to accommodate lower carbon fuels to manage vehicle growth while cutting emissions. The transportation modes we evaluated in our analysis are the shipping, rail, and trucking industries. Some of the fuels that are being considered to incorporate into the maritime industry include LNG, methanol, and ammonia. LNG is a widely available fossil fuel that is already used on many ships. It has significantly lower CO2 emissions than conventional fuels such as diesel and gasoline. However, LNG has a high methane content, so it still has a high global warming potential. Methanol is a single carbon fuel that can be derived from many feedstocks, including coal, natural gas, and biomass. It produces significantly lower CO2 emissions per mass of fuel than conventional fossil fuels. However, it has a low energy density by mass, so more methanol must be consumed to achieve the same power output. Ammonia is a hydrogen-derived, zero-carbon fuel that produces no GHG emissions when burned. However, the ammonia production process can be highly emissive when achieved using coal or natural gas feedstocks and when no carbon capture is used in the process. There are also many safety concerns about using ammonia as a fuel because it is highly toxic. Hydrogen was not included in our analysis because it is a very small molecule that is difficult to store and handle. During the production process of both methanol and ammonia, carbon capture and storage, or CCS, can be used to reduce the carbon footprint of these highly emissive processes. While more production facilities are moving towards the use of carbon capture, many still do not. For our analysis, we look at the life cycle emissions of methanol ammonia produced with natural gas steam reforming both with and without CCS. This brings us to the objectives of our thesis, which are to find the decarbonized fuel which has the greatest reduction in greenhouse gas emissions from conventional fuels in the maritime industry and to compare the relative greenhouse gas emission reductions of alternative fuels in the shipping, rail, and trucking industries. Now to look at some of the theory behind our thesis. Life cycle emissions in the shipping industry are referred to as well-to-wake emissions. This consists of well-to-tank and tank-to-wake emissions. The upstream well-to-tank process includes fuel production and transportation, and the downstream tank-to-wake process is the combustion of the fuel. For the measurement of emissions in our analysis, we looked to the revenue ton mile, which is the amount of revenue generated from transporting 1 ton of freight over 1 mile. This metric is commonly reported in the rail industry because often trains transport empty rail cars, which require energy to move but generate no revenue. We used a similar metric for our analysis, which we referred to as the emissions ton mile. This is the measure of the mass of CO2 equivalents expended from transporting 1 ton of freight over 1 mile. The unit we reported is the tons of CO2 equivalents per tons of cargo per mile. We will explain the CO2 equivalent unit later in this presentation. There are 3 aspects to the methodology of our thesis: the determination of routes and vehicle particulars, the life cycle cost analysis, and the opportunity cost analysis. We analyzed 3 routes to find the life cycle emissions of each fuel. The first route was along the west coast of the United States, from the port of Tacoma, Washington, to the port of Oakland, California. On the bottom of the slide, you can see the path the ship, train, and truck took along this route. We chose this route because the west coast of the United States provides a long stretch of straight line steaming, which serves as a good intermediate between short sea shipping and open ocean shipping routes. Additionally, the Union Pacific rail system allows extensive freight routes along the west coast. Moving forward in this presentation, we will be focusing on the Tacoma to Oakland route as an example. The second route was from the port of Hamburg, Germany to the port of Stockholm, Sweden. While Europe has an extensive passenger rail system, the rail freight system is more segregated in Europe than in the US. This is due to a greater number of international border crossings and rail systems. We chose this route because the long coast of Sweden allows for fewer international freight crossings in a direct rail freight route. The third route was around the east coast of Spain from the port of Huelva to the port of Barcelona. We chose this route because this is a single country route with a direct rail freight from Huelva to Barcelona, and because the ship passes through the Strait of Gibraltar, a high marine traffic area. For this presentation, we'll focus on the route from the port of Tacoma to the port of Oakland. For this route, we looked at a general cargo container ship, a freight train on the Union Pacific rail system, and a Class 8 semi-trailer truck. The ship is the largest mode, with the highest cargo capacity and greatest power output. The truck is the smallest mode, carrying a 40-foot container and having a cargo capacity of 2 TEU. As shown in the table, the distance along each route varies depending on the mode. While the distances should be comparable for each route, it is not necessary that they be equivalent because the emissions are measured per mile. Each ship we analyzed was unique to each route. However, we chose typical freight train and truck particulars and applied the same representative train and truck to all 3 routes. Here we show the Matson container ship, the R.J. Pfeiffer, which makes the Tacoma to Oakland route. The life cycle cost analysis evaluates the well-to-wake GHG emissions for each fuel type across the full fuel chain, from production to combustion. There are several inputs that are used to find the life cycle emissions of fuel. These inputs come from both the fuel properties and the transportation mode factors. The fuel properties we use to calculate the life cycle emissions were the fuel's energy density and carbon emission factor, which we will go over in further detail later in the presentation. The transportation mode factors included in our analysis were the cargo capacity of the vehicle, measured in TEU, both the propulsive and auxiliary power requirements, measured as the normal continuous rating, and the distance traveled, broken into the time spent steaming, maneuvering, and import. The percent NCR was adjusted depending on whether the ship was steaming or maneuvering, and powering was adjusted similarly for the train and truck models. Now that I've explained the model we used and established the inputs we require, I will discuss the methodology of finding the life cycle emissions. GHG is measured using global warming potential, which is the measurement of the energy 1 ton of emitted gas can absorb over a given time period. GWP is measured relative to carbon dioxide, and the global warming potential of CO2 is equal to 1. Global warming potential is quantified by the carbon dioxide equivalent unit. The table on the right shows the global warming potentials of common pollutants present in fuels: carbon dioxide, methane, and dinitrogen oxide. There are 2 timelines which are considered standard to measure carbon dioxide equivalency: 20 years and 100 years. For our thesis, we quantified global warming potential over a 100-year timeline, as this is the standard seen in the literature we used. The timeline is important because greenhouse gases dissipate out of the atmosphere at different rates. As shown on the table, the GWP of methane decreases from year 20 to year 100, indicating that methane leaves the atmosphere at a faster rate than carbon dioxide. Over a shorter term, methane-based fuels have a higher global warming impact. It is also worth noting that there's a low content of dinitrogen oxide in most fuels by mass, but because it has a high GWP, it still contributes significantly to the global warming potential of a fuel. To calculate the global warming potential of a fuel, we find the carbon emission factor measured as tons of CO2 equivalent per ton of fuel. To find the carbon emission factor, we first find the emission factor of each pollutant within the fuel. This is the mass of pollutant per mass of fuel. The overall carbon emission factor of each fuel is found by multiplying the emission factor of a pollutant by its GWP and adding up all the pollutants within the fuel. The carbon emission factor of each fuel is compared in this table. The energy content and ship fuel consumption for each fuel are also shown in the table. The baseline fuel for shipping is heavy fuel oil, for rail is diesel locomotive fuel, and for trucking is standard road diesel. DLF and SRD are different versions of ultra-low sulfur diesel. The alternative fuels are LNG, methanol, and ammonia. The table shows the fuel consumption and carbon emission factors when these alternative fuels are used on ships. There is a direct relationship between the energy content of the fuel and the amount of fuel that must be consumed to achieve a given power output. HFO has a lower heating value that is about twice the lower heating value of methanol. With a higher energy content, HFO is more fuel efficient than methanol in terms of mass of fuel consumed. This is a key factor when looking at the tank-to-wake emissions of a fuel. There are four main calculations we completed to set up our life cycle cost analysis. First, the specific fuel oil consumption in grams per kilowatt hour. SFOC is a measure of how efficiently an engine converts fuel into power. Second, the fuel consumption rate, measured in tons of fuel per hour. Third, total GHG emissions in tons of carbon dioxide equivalent. And finally, emissions ton mile, which is a key normalization to quantify GHG emissions associated with transporting freight, which is expressed in tons of carbon dioxide equivalent per ton cargo mile. Once the life cycle analysis was complete, we conducted an opportunity cost analysis to compare the different fuel and transportation mode options. Opportunity cost is a decision-making tool used to evaluate the potential benefits that are given up when choosing one option over another. Opportunity cost is quantified as the value of the alternative option minus the value of the chosen option. Opportunity cost typically compares economic costs, which are the explicit costs. For our analysis, we evaluated the implicit cost of life cycle emissions, found using the life cycle cost analysis. With this opportunity cost analysis, we quantified the differences between the emissions per ton mile of each alternative fuel across each transportation mode. I will now pass the presentation off to Phoebe, who will discuss our results.
Thank you, Lauren. To discuss the results of our life cycle cost study, I will utilize the analysis of the container ship that was applied to Route 1, Tacoma to Oakland, our exemplary case. First, the specific fuel oil consumption at each operating condition was calculated for HFO, the baseline fuel for the shipping case, MGO, a secondary fuel that we applied to our shipping analysis, and the alternative fuels, LNG, ammonia, and methanol. You can see that ammonia and methanol were analyzed two separate ways, synthesized with carbon capture and storage and without. It was important to separate these fuels into both options in this part of our analysis because the addition of CCS significantly affects the well-to-tank portion of our analysis. Second, the fuel consumption was calculated for each fuel as applied to the specific route for the ship. Third, the GHG emissions were calculated for well-to-tank, tank-to-wake, and combined well-to-wake emissions for each fuel type. Finally, the emissions ton mile calculation converts those GHG emissions, as seen above, into the final standardized measure. The well-to-wake values highlighted can then be compared against other fuels and further against other modes of transportation. After establishing our emissions profiles, our opportunity cost analysis was used to determine where each fuel has the greatest emissions reduction impact, and therefore in what industry it should be prioritized. Our focus is now broadened beyond the Tacoma to Oakland route, and these results are based on all the routes that we analyzed. This graph shows the ship emissions opportunity cost results. The y-axis represents each fuel type, which are all labeled on the right, and the x-axis represents the opportunity cost, which is each alternative fuel option subtracted from the baseline fuel. X equals 0, which is highlighted in red, represents the baseline fuel, HFO. Ammonia with carbon capture and storage has the highest opportunity cost because it is the most positive value, which means it has the greatest impact on emissions reduction. Although it's hard to see on the screen, LNG's opportunity cost is a slightly positive value. This means that without carbon capture and storage, LNG is significantly better performs than a methanol or ammonia without carbon capture and storage. The rail opportunity cost graph depicts a similar story. It is seen that the baseline fuel, diesel locomotive fuel, is represented as the X equals 0 line in red. Again, ammonia with CCS is the optimal choice. LNG and methanol with CCS have similar opportunity cost values and fall in second and third place, respectively, for the greatest reduction in greenhouse gas emissions. Again, ammonia and methanol without CCS present the lowest opportunity for emissions reduction. Because rail is already relatively efficient in greenhouse gas terms, there is less room for improvement overall, as seen by the generally negative trend. Trucking trends the opposite direction, as it is the least efficient mode of transport that we analyzed. So seen by the positive trend in the opportunity costs compared to the baseline of standard road diesel, there is much more room for improvement overall. The reduction impact of ammonia with carbon capture and storage is the greatest for trucking, as seen across all other modes. Because trucks start from a much higher emissions baseline, the switch to a clean alternative has a massive potential impact. Methanol, with or without the availability of CCS technology, represents the next best opportunities for emissions reduction in trucking. These findings reinforce the idea that optimization isn't just about emissions, but about context. The same fuel can have very different value depending on how it's produced and where it's used. The outcome for our primary focus, the shipping industry, is that if clean ammonia is available, it is the best choice. Meanwhile, LNG outperforms traditional fuels like MGO and HFO in shipping, so it becomes the most effective current alternative if clean ammonia isn't available. For rail, ammonia still comes out ahead with CCS, but without it, LNG or methanol become much more competitive. Because rail is already relatively efficient, there are smaller emissions reduction gains, and with all alternative fuel options overall. So this opens the door to research into different pathways such as electrification. Trucking, on the other hand, greatly benefits from switching to ammonia with carbon capture and storage, making it a prime target sector for decarbonization using clean ammonia or methanol synthesized with or without CCS. This highlights the importance of tailored fuel strategies, as each mode has its own optimal pathway based on current technology and emissions profiles. Our interpretation of the results led us to recommend the following fuel pathways. For shipping, we believe liquid ammonia with carbon capture and storage is the best recommended fuel to invest in. Based on research, case studies, and industry shifts, the infrastructure for powering rail is looking at alternative fuels, but also beyond. Rail is the most amenable to electrification based on these factors. For trucking, we recommend methanol as the main fuel pathway. It's important to recognize that while this table labels each industry with a unique decarbonization pathway, the production and use of alternative fuels will be intermodal, and our results ultimately encourage the investment of a variety of alternative fuel technologies and infrastructures for each mode of transportation. Even the use of ammonia in these industries will ultimately lead to the use of hydrogen fuel cells, which is a promising energy source for shipping, rail, and trucking in the future. It was also validated in our study that LNG is most practically defined as a transition fuel that will prepare transportation industries for cleaner fuels like ammonia and methanol further down the line once there's greater supply and technology is furthered. We determined that ammonia synthesized with carbon capture and storage resulted in the lowest greenhouse gas emissions per ton mile across all modes. However, that's only true if ammonia is made using carbon capture. Without it, ammonia becomes the most emissive pathway due to its high upstream production emissions. This is a critical distinction. Since conventional ammonia synthesis, often through coal gasification, is extremely carbon intensive, until clean ammonia is viable, other options will continue to be defined as more practical. This shows that the production method is just as or sometimes more important than burning the fuel itself. In conclusion, we found the fuel that makes the biggest impact on emissions reduction in each mode of transportation, and the results we achieved are in line with industry, research, investments, and trends. The impact of this analysis is represented in the broader implications for fuel planning across the transportation industry. The biggest insight from our work is that there won't be a new universal fuel like diesel. Each transportation mode will need to adopt different varieties of fuel solutions, depending on what's most efficient and sustainable for their specific operations. Each transportation industry has its own unique characteristics, and as fossil fuels are phased out, the transportation fuel landscape will continue to grow increasingly more diverse. Since single fuel standards will no longer be practiced, fuel allocation must be strategic, not just based on emissions, but also on resource availability, infrastructure readiness, and regulatory and economic factors. While it's clear that ammonia is promising, carbon capture and storage must scale up in order to realize its full potential. Looking ahead, there's a lot more that can be done to build on this study. There's room to study new fuels like biofuels, hydrogen, and blended fuel strategies. There's also the option to increase the fleet by analyzing more vehicle types or scaling the fleet size to get a clear picture of global impacts. Or an economic opportunity cost would provide insight into which fuel choices make sense, not just environmentally, but financially. And the opportunity cost model could be expanded to incorporate emissions like particulate matter, or beyond emissions to incorporate fuel availability and production constraints, or integrated regulatory constraints and penalties. In closing, this project provides a blueprint for how life cycle and opportunity cost analyses can guide smarter, more sustainable fuel transitions across all of transportation, and hopefully gives you a glimpse of what will likely be powering the ships, trains, and trucks of the future. Thank you for listening, and we please ask that you hold any questions until after Hendricks has finished presenting his thesis.